Okay, so we're moving on, and in a previous video, we derived the probability distribution that arises from a single constraint, the normalization constraint. And we saw there that we came away with the normal distribution. And in that video, we discussed this idea that moments could be constraints, and that we could treat the normalization constraint as the zeroth moment. Well, now we're going to look at some other moments as constraints. And we'll get into a little bit more detail, but for now, the basic idea is that these moments encode certain features about the probability distribution. So when we are constraining certain moments, we are inherently constraining certain features about the probability distribution that we are deriving. So remember that moments are simply the expected value of y raised to the kth power. So the the kth moment is the expected value of y raised to the kth power, and you can do this for discrete and continuous variables. Okay. So what you're seeing right there is the population moment, or the theoretical moment of the distribution. Okay. But what we will often do is we will, in our constraint, we will set the theoretical moment equal to the sample moment from our sample data. Okay? And so we take the sample moment by basically raising every observation to the kth power and dividing by the number of data points. So we're taking the average. Okay? So why do moments matter? Well, like I was saying at the beginning, moments encode certain features of the probability distribution. So for instance, the first moment is the expected value of y, which is the mean of y, which is often represented with the Greek letter mu, right? So the first moment encodes the mean. It encodes the central tendency or acentral tendency, or you might call this the location of the distribution. The second moment, the expected value of y squared, when combined with the first moment, we can get the variance or the spread of the data. Okay, and you can hopefully follow the equations there in that box. And then as we add higher and higher moments, we can we can derive more features about our distribution, right? So if we have the third moment, we can get to the skew. If we have the fourth moment, we can get to the kurtosis, so on and so forth. Okay? Now, what's important is that these moments that we are choosing to constrain they're an assumption that we're making about our data. That's what it is. We're saying that these moments are relevant for our data generating mechanism. Okay? And then what we get in return is the probability distribution that makes the least assumptions outside of that it has these moments and that they're relevant and that they are assigned to particular values, right? And those particular values, like I said before, are what we find in the sample. Okay? So we're saying that the theoretical distribution has the kth moment equal to the kth sample moment. Okay? Just a small caveat about that right now. We will later find ways to use something other than just a point estimate from the sample data. So we can set our constraint not equal to a sample value, but to some other value that we may think is a better estimate. So I just don't want that to be a concrete rule, but for now that's what we're going with. Okay, a couple important things about moments. So not all distributions have all moments. Okay, you can imagine that if you take y to a high enough power, well then its expected value just becomes infinity. Okay, so for instance, the normal distribution has all moments, but the Cauchy distribution has no moments. And if you need a better explanation of that, there's an appendix in the online course. But for now, you can just take my word for it. It's not really relevant to where we're going here. And another thing to know about this is that if one moment exists, then all of its lower moments exist, but not necessarily higher moments. So for example, if we have a distribution where the third moment exists in the theoretical distribution, we can be sure that the first and second moments also exist, but we cannot be sure that the fourth or higher moments exist. Okay, so these are just things to keep in the back of your mind about moments. Okay, the possibility of moments not existing becomes more relevant with heavier tail data. So in other words, very how do I want to say this? Very data with a lot of possible values. I guess we'll put it that way. Okay, so. And because of that, there's something very important that you need to be aware of. We just stated that not all distributions have all moments. Okay. However, given a sample of data, you can compute every moment. All right, because you have a finite sample of data. Okay, so for almost every sample, you can compute every moment in your sample distribution, in your sample moments. That does not mean, though, that the theoretical distribution actually has those moments. Okay, the reason that this is important is, you might just say, well, why not just define as many moments as we want? I mean, we'll constrain, to the 1027th moment, and then I'll get tired and don't want to do any more. Well, the reason is because every assumption that you're making that these moments exist may actually violate the true data generating mechanism. So it pays to be conservative with the assumptions that you're making, right? This is just a general rule of thumb for all critical thinking, really. But we see that manifest here. Okay, so once we identify the moments that we assume are there, there's an easy way to just encode them as constraints, right? So we already saw this with the 0th moment, right? So we had the 0th moment. The expected value of y to the 0 equals the expected value of 1 equals 1, and then we just export that over to moment 0. I don't really have a laser pointer at my disposal here, but hopefully you can follow the arrow over and kind of see what the pattern is. And similarly with the first moment, right? The constraint just becomes the theoretical moment, which is the sum of y times p of y. Okay, that's how you take the mean, the first moment, okay, minus the sample moment. Okay, and you can do that for every moment, all the way down. And again, for continuous distributions, then we're using integrals instead of sums. Okay, so let's actually plug in this mean constraint. Now, in the previous video, our Lagrangian looked like this, right? We had the entropy term minus lambda naught times the normalization constraint. And again, what that normalization constraint is doing is it's assuring that the probability distribution sums or integrates to 1 or 100%. Okay? And so adding this additional constraint is as simple as adding this additional constraint, just like this into the Lagrangian. Okay, that's all we're doing here. Okay, so think about what this is doing. So this constraint is saying that the theoretical constraint, the sum of y times p of y, which again is just the theoretical mean of the distribution, minus the sample mean is 0. That's all that's happening here. Okay, so again, how this plays out through the math is the theoretical distribution that we generate will have the mean of our sample first moment. Okay, and again, I'm just flagging this for later videos. There will be other ways that we can estimate M1 hat in this case, right? So that is not a hard and fast rule, but it's a simple rule for us to follow right now. Okay, and of course, this new lambda 1, this is a new unknown in our distribution, and we will go to solve that, right? So this new Lagrange multiplier, lambda 1, is controlling how important the mean constraint is on the overall distribution. So when we go to now solve for p of y, so hopefully you remember this from the previous video where we had the very simple case, but we take the derivative of the Lagrangian with respect to each p of yi, and here we get well, the expression that you see right there. that is identical to what we saw in the last video, except for now we have an additional negative lambda 1 yi. We set that to 0, we solve for p of yi, and we get that expression on the bottom of your of that box there. Okay. And then there's a little notational trick that we will employ, and that is to call the e to the negative 1 minus lambda 0. We're going to call that z, right? So notice that that term, or that part of the term, has no dependence on y. Okay, so we just call that z, and it makes it easier to work with, right? That's so again, that's just a notational trick. It makes things easier to work with. All right. So again, the rationale for this is that the normalization constraint does not depend on y, and so we can, we don't have to, when we're trying to find the probabilities of the y of each yi, z is not affecting that, so we can just pull it out and treat it as its own term there, and it makes things look nicer. Okay, so we're going to continue to solve this analytically. And so we're going to try to solve for z. We could also solve for lambda naught, but we pulled z out because it makes things easier. And the way that we do this is we bring in the normalization constraint. Okay. So remember, we have from the previous slide, we have as many derivatives of the Lagrangian as we have data points, right? And each of those is an unknown. But now we have two additional unknowns. One is lambda naught, or in this case it's z, or lambda naught is packaged in z, so we'll just solve for z. And then the other additional unknown is lambda 1. And so we need two additional equations, and one of those additional equations is the normalization constraint. Okay, so hopefully you remember that from the previous video. And the other equation that we have now to solve for lambda 1 will be our second constraint that we've just imposed. Okay, so to solve for z here, you can see the steps there at the bottom of the screen, or in the middle of the screen on the left-hand side. Okay, but in this case, we come out with a final expression for z. You don't have to remember that. I'll show it on the next slides. But it becomes important because we will then use that as substitution later. Okay, but this is how we solve for z. We get z in terms of lambda 1, right? So whereas we had two unknowns, z and lambda 1, or maybe you call it lambda 0 and lambda 1, but either way we have two unknowns. Now we have one of those unknowns in terms of one unknown, lambda 1, right? So we've simplified things so far. And now to solve for lambda 1, like I said, we bring in our new constraint, and we solve for lambda 1 in this case. Okay. Now, what we have right here is as far as we can go right now. We'll be able to continue here in just a second, but because we have failed so far to give y boundaries, right? We don't know what the bottom and top values. We don't know the possible values of y. And so to continue, if we're going to sum over y, well, we need to know the possible values of y, right? So what we have right now is just a generic form. And once we know the bounds, which if this was a real problem, we would already know the bounds, right? But we're discovering this as we go along. Okay. So let's give it some bounds. And because it's simple, we're just going to use a binary case, right? So y can be either 0 or 1. That's it. That makes the sums very, very easy. So if you look in that teal box right there, right? It's very easy to take that expression and sum, y equals 0 and y equals 1, add those together, and you get the expressions there that you see that are presented. Okay. So at the bottom of the teal box, we have the probability of y given I, where we've effectively taken the sums. Okay, and now we can use that back to solve for the moment, right? Because what is the moment? Well, it's the probability of y times y. And so if you carry out that math, you come out with lambda 1 equals the negative logarithm of the first moment, or estimated moment, divided by 1 minus the first moment. If you want to, hopefully you can do this math on your own, but certainly if you want to see the step by step, it's in the full online course. I don't really know how important that is, because the whole purpose of this is eventually to say, oh, but in most cases we should rely on numerical derivations, where these analytical derivations just aren't that important. So now think about what we have. We have an expression for z and an expression for lambda 1. And so we can plug that into our intermediate form of the probability distribution, which was z times e to the negative lambda 1 yi. And I'm skipping steps, for the reasons that I just mentioned. You can certainly do them or look at them in the full online course. But when you go through and you complete all those substitutions, you come out with that expression right there. The m1 hat to the yth power times 1 minus m1 hat to the 1 minus yi. And if you consider the fact that m1 represents the mean, this is the Bernoulli distribution. Okay, so again, this just fascinates me about this whole MaxEnt setup, is that we start with this very foreign-looking thing, this Lagrangian that has all of these terms, and we push through and we push through, and we come out with a recognizable probability distribution. It's so beautiful. It is just so beautiful to think about this, that these probability distributions, even though maybe the people that were deriving these things weren't thinking explicitly in these terms, they were preserving maximum uncertainty and knew that that was a principle that they needed to uphold. It's just beautiful. But anyway, so when we push through all of this, we get to the Bernoulli distribution. Okay, so what does this tell us? So if we have binary data and we just assume that it has a mean, and it's normalized, of course, then the highest entropy distribution, the one that allows us the most uncertainty, is the Bernoulli distribution. Okay, it just emerges out of that single assumption, and like I said, it's lovely. Okay, now this is another instance where we were able to solve it analytically, no problem, but we could also solve this numerically. But of course, if we knew that our data abided by the assumptions of the Bernoulli distribution, then we should just use the Bernoulli distribution rather than derive it from scrap. But nevertheless, if we're going to solve this numerically, we again define a loss function, which is just in this case our constraints squared, right? Because our constraints are written as these residuals. We write a loss function that way. And then we tell R, in fact, the command optim, or whatever analogous command that you're using in your software, but we tell the computer, I'll say, to evaluate this loss function. So here's the loss function in the orange over here. It just translated from the mathematical notation on the left-hand side. We tell the computer, minimize these values, and it outputs estimates for all of the unknowns. And in this code, the unknowns would be z and lambda 1. So we'll get estimates for that. But again, we could have used a slightly different expression for the probability of y, right? Because there was a time where we found z in terms of lambda 1, right? So we could have used a slightly different expression, right? And so we could have boiled down that whole loss function to just finding lambda 1, and that would have also been absolutely okay. If that's going a little bit fast and going a little bit over your head, again, check out the online course and you can kind of have that explained a little bit more depth, but hopefully that makes sense. So in this binary case, it was rather simple, and we chose it because it was very, very easy to just brute force these sums. Okay? But if we have, for discrete data, if we have different ranges of our data, then we need to take brute forcing it often becomes too difficult. With a computer, you could probably code it up, but we can also write analytical expressions for this. This is sums of geometric series. I'm not going to talk about that here, but there is an appendix in the book, or there's a lot of very fine resources, like on Khan Academy, for instance, of how to take these very large and burdensome sums of geometric series. Okay, so now we shift very temporarily into incorporating even more moment constraints. So what you have there is a Lagrangian with the first 4 moments as constraints. Okay. Now, conceptually, nothing is really changing here. We still go through the same process, but what you will find in trying to, you can go ahead and try, but as you go through and try to solve this analytically, problems like this are either impossible or at least very, very hard to solve analytically. And again, this is where numerical methods become indispensable, really. So, if we assume then that we are dealing in the continuous data realm, okay, our moments now look like they do in that teal on the bottom left there. Okay, so it's y to the k times the probability of y, and we just integrate over all values of y minus the sample moment. Okay, but like I was saying, there's no real analytical form for this, and so we need to instead use numerical workflow. And so I'm giving a kind of a mock representation, really just so it fits on the screen. But really nothing, again, nothing conceptually is changing. We still generate a loss function where it's just our constraints squared, and then we pass that to Optim, and we ask, or whatever software you're using, and ask the computer to please find estimates for the unknowns. And here it's going to be your lambdas. Okay. But you're also going to hit a wall here. Okay. Oh, I see that there's a typo up here. Just ignore that. And the problem is this. If you just try to use the loss function that we saw on the previous slide, some of those moments get very big, right? So when we're at the 4th moment, we're talking about very large values. Okay, so if y is 4, then y to the 4th is 256. Okay, well, what if y is 100? Well, okay, well, now y to the 4th just becomes unmanageable. And what this causes is something that we'll just generally refer to as numerical instability. Okay, the computer will not be able to come up with adequate estimates. And so that is one cause of numerical instability, and there's several other causes that we will encounter, but this is really the end of this video and the launching point to the next several videos where we look at some tricks to get our computer to stably estimate our unknowns.